I have the pleasure of introducing Professor Lindsay Anderson today, who's our Jones Seminar speaker and is visiting us from the Biological and Environmental Engineering Department at Cornell University, and I learned that she's part of many other departments at Cornell as well. Professor Anderson is the Norman R. Scott Sesquicentennial Faculty Fellow, as well as the Kathy Dwyer Marble and Curt Marble Faculty Director for Energy within the Atkinson Center for a Sustainable Future at Cornell. Her research interests focus on systems modeling and optimization applied to energy and environmental systems and problems. Her research goal is to accelerate the transition to a low-carbon energy future, and I believe you can tell from the title of her seminar that we'll learn today how will we get there from here. So with that, I'm pleased to introduce Professor Anderson.
Okay. Thanks very much for the intro, and thanks to all of you for being here, even some familiar faces from Cornell. That was a fun surprise. I forgot you were here. So what I'm going to talk about today is really what are some of the challenges of transitioning our energy system. I've had a really fun day of talking to all kinds of people who are working on all different angles of this problem. So today I'm going to talk about at least my angle on this problem. I like to put my acknowledgments at the front because quite often, we get to the end and we're out of time and there's no time, we're answering questions. So I just want to make sure that I get a chance to acknowledge some of the collaborators and students that I've worked with in my funding agencies over the years. I'm not going to talk about all of our projects, but I'll touch on a few within the general context of this talk. I like to start out by sort of making the case for why we care. After all my visits with everybody today, I realized that I probably don't have to make this case here, which is a wonderful situation to be in. But I like to have this slide to sort of remind all of us that there is actual observed impact from climate change. This is from the IPCC's AR5 report. And the point being that all over the globe, we're actually seeing impacts of climate change. In particular, I know that a lot of people here at Thayer and at Dartmouth more broadly are working in the Arctic, and that's where we see some of our most important climate change impacts that we know are a result of anthropogenic activities. Okay, and so this is also from the IPCC report showing sort of this black line here is the historical emissions, and we can see that the IPCC sort of took a look at sort of all the potential scenarios of the future from other people's models and reports, and sort of show a band of where we might go over the next century, right? So we have a business as usual. We have the RCP 8.5, which is sort of our worst case scenario here. And the 2.6 is what we might hope to achieve if we really get ourselves in order in the very near future, right? And looking at, each of these scenarios, where are we looking over time at the total temperature change relative to the baseline in 1880, right? So looking at the kind of emissions that we're seeing versus the kind of temperature change that we'll observe. Which leads them all in this particular report to say, okay, well, this is the observed temperature change that we've had so far, and these are the sort of two bounding scenarios, right? So best case, we're looking at something like this, which is still warmer than it is today, right? But it's not nearly as extreme as this scenario over here, which is just the nightmare scenario that we do not want to lead to. Based on that report, the IPCC then tasked the team to look at what do we need to do to really limit our warming to 1.5 degrees C, right? How are we going to keep ourselves here? And that working group did a really deep dive into what would be involved and whether we could actually do it or not, right? So how are we going to be able to limit that warming, not even into the undetectable level, sort of between the moderate and high, right, is the best that we can shoot for in this case. And then this comes from the National Academy report that actually took the 1.5 degree report and said, okay, what do we actually have to do to get there, right? So you can see here what we've got is greenhouse gas emissions versus time, right? And this sort of looks at the different approaches that we're going to have to take here, right? So the business as usual is our yellow line, and how are we going to get here to keep ourselves below 2 degrees C? Okay. Quite clearly, we're going to have to come up with conventional abatement technologies. How are we going to mitigate our carbon emissions, right? So we're going to change the way we behave. We're going to actually capture. We're going to reduce our emitting technologies significantly. And even with all those, even if we do all those things right, we're still going to have to figure out how to take CO2 out of the air. Right? Even if we do everything that we need to do and we all change our lives completely, we're still going to need to be able to actually do net negative greenhouse gas emissions to make that work. And it's going to cost us money. It really is, right? Where are a lot of those coming from? So this is the global CO2 emissions, right? Sort of attributable. This is up to 2000, so it's a little bit older, but how we're trying to attribute it. And the only point I want you to take away from this slide is that the bulk of those emissions are from fossil fuels, right? Which leads us to the conclusion that really the biggest key player here is going to be able to decarbonize our energy system, right? And our energy system is something that's not it's not optional, right? Our entire society and our economic success or resources are all dependent on this energy system. So that's why I choose to focus on the energy system in general. This is greenhouse gas emissions from electricity production over 1990 to 2015. This is the electricity generation, so you can see generation is growing as we know it does, right? We have an increasing demand, and you can see that, coal was starting to tail off, right, even here in 2015, and we were starting to increase our natural gas generation, right, which was seen as sort of a clean transition fuel, also had the benefit of becoming really inexpensive, right, which had a tendency to derail some of our other efforts. Nuclear was pretty stable. And renewable, again, sort of starting to grow over here towards 2015, but really not a big enough piece of the puzzle just yet. We've seen sort of an increase in regulatory and climate drivers here, right? So this is in no particular order. Some are still alive. Some have been killed, in particular the U.S. Clean Power Plan, which I thought was a fantastic thing that's off the table now. But there's been a lot of regulations and changes. So the IPCC has played a really big role in this space, right? Really doing the research across political borders and then communicating the urgency of the situation. The U.S. Clean Power Plan was set up to really help us with decarbonizing, at least cleaning up our power grid. And then the state level renewable portfolio standards that have been around for a while. And then you've seen sort of in the last year or 18 months, all these sort of state, city, community level commitments and aspirations to carbon neutrality goals and growing policies around the world, right? So this has led to some investment, or quite a bit of investment in renewable energy across the world. Quick glance at the map of what are the renewable energy policies around the world. So most of these things that have a dark green color have more than one policy type. So they might have a renewable portfolio standard. They might have renewable energy targets. They might have demand response programs, but more than one sort of thing here. But you can see there's also countries that just sort of have a feed-in tariff. So this light blue color says, oh, if you have renewable energy, then you'll get a guaranteed rate, for example, to try to incentivize investment in development and so on. All coming, so a whole portfolio or menu of different things are happening. And then I already alluded to this, in the last year or so, we had so much going on in this space, right? So, I love this title here, right? This headline that says it was the year of 100% clean energy. Because despite what's been going on sort of at the federal level, at all sorts of other levels, the people have been making plans, right, to go to 100% renewables, looking at grid integrated buildings. I talked to somebody earlier today who's really interested or had worked in this space. This idea of our new smart homes and Sense working together with your Alexa or with your Nest or whatever, so you can say, hey, Alexa, how can I save energy how can I save money on my energy today, right? Or how can I reduce my greenhouse gas footprint? Which, sounds kind of silly, but it actually really works. About a year ago, I was giving a talk to an alumni group in Long Island, a Cornell alumni group, and And I can't remember how we got on the topic, but somebody came up to me after the talk and said, you know, I have solar panels on my house, and I have this app on my phone, and it tells me how many CO2 emissions I actually avoided last month. And the person standing beside me said, yeah, I have mine too. I did better, right? So it's like, it sounds kind of silly, but there's all these kind of really fun mechanisms. And in my group, we started calling it, energy with friends or carbon with friends, in case you could have a game. So anyway, so there's been lots of some really, really exciting stuff going on sort of in the news lately. And when I spoke to the students at lunch today, we sort of talked about what does that mean if a community says, oh, we're going to be 100% carbon-free in Hanover or in Ithaca, right, by 2030. How are we actually going to do that, and what can we control and what can't we control? Okay, so with all these policies, right, we see a lot of investment in renewables globally. So who's winning here? So far, we see China obviously has been investing massively in renewables over the last decade or so, maybe not that long, last 5 years, as well as developing and emerging countries, right? So a lot of them are investing. A lot of this has to do with rural electrification as well, how they're investing there, and then looking at what the developing countries are doing. So you can see here that it's, this is just the world total of investment in renewables over that time, and it bounces around a little bit based on sort of economics, right? You can see there's a couple dips here around the recession and then like some mini economic downturns in here, but by and large, it's kind of growing. Where is it going, or how are we using it? So this is kind of an interesting question to me. So this is the renewable share of electricity consumption, right? This is what we consume at the end. And you can see here it's still almost 80% fossil fuels, right? We still got a little bit of nuclear. We've got traditional biomass as well as biomass down here and solar for heat. And modern renewables only being about 1.7%, right? That doesn't actually match with what some of us read in the news or what we believe, right? But the important thing is that this is the end use consumption, right? So it's a fairly small amount. There. And then, wait a minute. That's, energy consumption. And then we move to electricity consumption. That's what I was looking for. So you can see that this number has gone down, right? Because what have we taken out here? When we talk about energy consumption, we're still talking about transportation systems, right? Now we're talking specifically just about electricity production, and you can see renewables look much, much bigger here as a fraction of the actual electricity we generate, though hydropower still really dominates, right? And wind looks bigger because we basically only use wind energy for generating electricity, right? And then that's all I wanted to say about that. Okay. This is the point I was going to make here, and the difference between those two is that we still really, you saw in the difference of those two charts, is that the first one is in consumption, and the second one is in actually electricity, right? So energy versus electricity, and you can see from looking at this chart that if we're going to, I love to think about power. Electric power is what I do, right? So obviously I'm going to talk about that. But the key things we can't forget about are heating and cooling, right? A lot of the heating, we use natural gas. So that's going to be a big part of our carbon footprint. And how's that going to work, actually, when we say, you know what, we're not going to heat our homes with gas anymore, so we're all going to plug in. Right? We're all going to plug into this energy system that we're also going to put a whole bunch of variable renewables on, right? So we're adding stress at both ends, but it's got to be done because there's no point in decarbonizing this 20% and leaving the rest, right? We don't get what we need from that, okay? And the same with transportation, right? So we got a small amount of biofuels going into transportation. Again, we can electrify transportation. I think it's a great way to go. But we have to figure out what that's going to look like on our electric power system and how we're going to manage that. The good news is that when we add heating and electric vehicle charging to the electric grid, it has the potential to add a bunch of stress. It also has the potential to add a bunch of flexibility that we can use. Okay, so I just want to talk for a couple minutes about about particular renewable energy sources and what their challenges are. So this is just the growth in wind to convince you, which you probably already know, that wind is actually really growing. And in fact, offshore has been increasing even more quickly and more recently. And then here is solar PV. And I think over the last sort of few years, solar has really, really taken off. And they're actually putting in larger solar PV plants, right? So at first, it was a lot of behind the meter stuff, but now we're seeing not just behind the meter, not just rooftop solar, but also community solar and large scale solar. And Asia has been investing hugely in this space. Geothermal. Geothermal's been getting a little bit more press lately. I saw something in the New York Times yesterday that they're looking at doing some geothermal in the UK. So this looks at geothermal for electricity production. Okay, and there's a couple different ways we might want to think about geothermal. Geothermal has a lot of potential in this heating and cooling space, right? So if we have a really great thermal gradient, right, we can dig a hole, we can get really hot temperatures from down there, we can create steam, we can run a turbine, and we can get electricity out of it. But if we don't have a super high temperature gradient, we have sort of moderate gradient, we still have some heat exchange capabilities right there. So that can answer actually quite a lot of that heating and cooling load that we were talking about that isn't addressed necessarily by the electricity system, right? But this is not for heating. This is just for geothermal electricity production, which the United States actually had been investing quite a bit. And I've seen some stuff in the news lately that this is also growing. So the whole point of all this was like, we got wind, we got solar, we got biomass, we got geothermal, right? We have all the pieces we need. I've told you why each of them is excellent. And they're growing. So my question is, so why can't we just replace all the fossil generators with renewables? Right? I just told you. We have all this stuff, right? And if you look at some of these reports, they'll say to you, actually, we have enough potential power from wind, from solar, from hydro that we can just meet all our needs, right? But we can't. And the reason we can't is this. Probably half of you have seen this before. It's still one of my favorite plots, right? So this is from what was originally, well, anyways, 3 tiers, somebody else now. So this is a wind map, right? So this says, it looks at what the variance from normal is in wind speeds across the US. So this is the departure from normal in percentage for the year of 2009. Okay, so the red, the hot colors are a little higher than normal, right? If you had like dark red, it was 10% higher. And the cool colors are lower than normal. And then this is the first quarter of 2010. So tell me where you're going to build your wind farms. Right? It's kind of unclear. So you go, oh, well, actually, these ones here, they're much higher. So let's do that, because it's dark red. All right. Second quarter. Right? I mean, this isn't news to you. I know that, but it's funny, right? Because it's stark. That if you look at this map, or you look at the previous map, or you look at, like, in one quarter, you've completely flipped over where your wind resources are available, right? So there's a lot of variability year to year, season to season. But that's not even half the problem. This is the other half of the problem, right? So this is intra-day variability. This is just some Nantucket wind speeds, right, when we were talking a lot about the Nantucket offshore wind farm. And these are wind speeds over just a couple months here, okay? So a lot of the talk about how we can just use wind to replace our coal comes from the situation where we take something like this and we say, well, this is the diurnal average. We can work with this, right? The problem is, in electricity systems, you have to instantaneously match what you're producing with what you're consuming. So planning to use this and you get this is very bad news, right? It's bad news for blackouts. It's bad news for equipment. It just won't work, okay? We're getting better at forecasting, but there's still a lot of uncertainty, right? So we can deal with variable if we could predict it, right? So one of the things is how well we can forecast. So this is not my plot. This is from Pierre Pinson, who makes the most beautiful plots, I have to say. that looks at the wind speed forecast. It's an example. This is data that they've pulled together. And the white line is the predicted wind speed, right? And the gray give you confidence intervals on those wind speeds. And the black with the markers is actually what was observed in the end, right? So we can forecast pretty well at very short time scales. You can see over here we're not too far off, right? So this is sort of in the sub 5 hours. But does anybody know how far ahead we have to plan some of these things for power systems? Not investment planning, right? Investment planning is decadal scale. But even operationally, right, we have to decide which generators we're going to turn on for which hour of the day 24 hours ahead, right? And 24 hours ahead, we still have a lot of noise here, right? There's a lot of uncertainty. So if we take off right away and say we're just gonna use wind and solar, right? And solar has a lot of the same issues. It's a little bit more predictable, but it still has a lot of variability. Then how are we gonna meet those needs when unexpected things happen, right? So that's the major challenge. So as I said, solar has the same problems. I'd be surprised if most of you hadn't seen this, but this is just to sort of show this other thing that's kind of important, right? So this is net load March 31st, for example, in California, 2012, this is what they observed, and 2013, this is what they observed with more solar coming online, right? And this got people thinking, oh, wait a minute, so as all this solar comes online, this net load, right? So net load is the forecast of or the load that you need, right? How much power you have to provide to your consumer, less how much renewable. So in this case, less the solar that's on the system, right? So it's great because the sun is shining and the solar plants are producing, right? And we're dipping lower and lower and lower and lower and lower. Okay. Here's the problem, is that we have other generators on the system, right? And those generators can't be turned off with a flick of a switch. Right? They have to be ramped down. They can't really be ramped down to zero production if you're still going to need them again later in the day. And you can bet you're going to need them because then as soon as the sun goes down, you're facing this huge ramp right up the other side. Right? So you need to have resources available here to manage that shortfall as it comes. And the concern with this duck curve is the unprecedented rate of ramping. Right? So we need generators available or resources. Right, we need resources available that will be able to quickly ramp up and down so that to balance that out. Okay, so this, I think I'm gonna, how am I for time? This was just to explain really how the timing is important. The important thing is that at the day ahead, 24 hours ahead, the system operator has to look at their forecast for the load for the next day and decide what generators do I need online for which hours to manage my forecast, right? So if you have a lot of wind in your forecast, you can't really control those within wide swings, right? And so you have to think about what you might need, and those decisions have to be made well ahead before you actually get to update your forecast with this short-term, more accurate forecast. And then you need something to be able to balance it in real time. So I don't want to focus too much on this, but this was to remind me, essentially, to explain to you why making decisions within the real time or the really short time scale when our forecasts are much more accurate is actually not possible for the bulk of our generators on the system. Okay, so storage, that's usually the next thing that comes up. People say, well, why don't we use storage? So I kind of wish I hadn't put many, because I also believe that viable large-scale storage will be critical to this transition, or it certainly will facilitate, right? So there's a lot of people working on storage in a lot of different ways, and pumped hydro storage obviously is something that we have well developed, but it requires very specific geographies to make that work, right? Utility scale batteries I talked about with people today. We're not at a good place that it's really viable economically yet. Certainly if we had those, that would be a game changer for our storage. But we really have to think about the ways in which we operate the grid if we had storage, utility scale storage around. which is what I spend most of my time thinking about. And then there's also distributed storage, right? So we think about sometimes people think about vehicle to grid, so this idea that we could take electricity out that's stored in cars and use it in the grid. But even a first step for that would really be allowing us to leverage the flexibility, right? So I was telling a few people today that in Ithaca we have this test bed that's running this electric car charging, right? So it's a simple program that's within a pilot program that we have in Ithaca in the test bed. And what it does is they're collecting data on baseline right now, but the plan is that when you plug your electric vehicle into charge, you tell the app when you need your car charged for. So if you give 12 hours, you're going to pay less for that electricity than if you give 2 hours or 3 hours, right? So you're sort of being rewarded for providing that flexibility to the grid to be able to charge more or less depending what the current situations are. So even though I'm not proposing that we take energy out of the car battery and use it to serve the grid, there are ways that those distributed storage capabilities could be used. But you can see here that most of the existing storage that we use right now is still pump storage, right? We really haven't leveraged or haven't found that silver bullet yet. Okay, so I've talked about how important it is. I've told you how hard it is. And now I want to talk a little bit more about how we might do it, right? So we're all about flexibility. So my big argument is that the electric power system is really the only market in the world. I'm sorry, I know I said this like 3 times to people today. It's the only market in the world where consumers have no idea how much they're paying. Okay, except for you guys that are on Green Mountain Power. You guys are all very well informed. But most people in most parts of the country have no idea how much they're paying, right? Or how much they use even, right? So I have this friend that I was at a talk that she gave once, and she said, so how many of you guys know what the gas prices are in the 3 closest gas stations to your house? Right? Everybody puts up their hand. Okay, how many of you guys know how much you're paying for electricity? Silence, right? Not you guys. I mean, you're really well informed. But by and large, people just don't know, right? And if you raise the prices, there's no response, right? There's zero elasticity. So we've operated this system with absolutely no consumer participation, except when the utility goes to the Public Service Commission or whatever the regulatory structure is and says, we need to raise rates. Then we start to see some consumer participation. But what we really need is for people to engage with energy in their lives, right? This is my argument. So we can really accelerate decarbonization if we get consumers to participate. So there are existing programs. There are some residential pilot programs. We were talking last night, and these programs are really actually growing. There's quite a lot of commercial industrial type programs, and these emergency response programs where the system operator will send out an urgent signal and people will reduce their load. These are things that exist or are developing. But what I'm talking about is automated demand response, right? I'm talking about your hot water heater, right? You're here. You don't actually care if the hot water in your hot water heater has dropped a few degrees, right? Until when? Like till you do your dishes tonight or something, right? I'm talking about your air conditioner, which you could cycle on and off on a pretty high frequency scale and not really notice any comfort, right? So if we could leverage those things, because they're right where we need the flexibility, right where the loads are. And then we think about, even the idea of sort of distributed energy resources more broadly, right? So I guess I said these things, but washing machines that you can delay the start for a few hours, right, into the evening, hot water heaters, air conditioners, plug-in vehicles. I've already made my case. I keep getting ahead of my slides about why I think plug-in vehicles can provide flexibility, as well as rooftop solar PV and residential scale battery, which seems to be a growing area. Somebody was telling me that Green Mountain Power is running a pilot here now where they essentially give you the battery to work with your solar in exchange for them being able to control it. So, and then if we can sort of connect these things with some sort of controllers in our home, and this is just it's not for real, but you could actually sort of do this in a really easy and perhaps even fun way, right, that would support the system transition. These things are growing for sure. Behind the meter storage, it grew in the last couple of years and is projected to grow huge. I mean, everybody's been predicting batteries to grow huge for a long time. Smart meters, definitely, right? This is only 2020, and these things are all being deployed all over the world. If you look at the electric vehicle sales, though I understand Tesla's electric vehicle sales fell for the first time this quarter, but Asia Pacific shot up, so I think Tesla's happy. I heard they actually made money. And smart appliances. Yeah, so these, your appliances that, it have something as simple as that you could delay the start, or as complicated as you could have some sort of automated signal response. Okay, so hopefully you're convinced that there's lots of untapped flexibility there, right where we need it. The question is, right, I just told you things are hard and I made them harder, right? How are we going to manage under increasing uncertainty? Because not only you have uncertainty now in your renewables, you have uncertainty in your consumer response, right? If I tell everybody in Hanover I'm the system operator and I want you all to reduce, how many will respond? We don't know. There's no historical data there, right? So we're introducing uncertainty there. How are we going to coordinate these things, right? How are we going to coordinate them? While protecting people's privacy. Right? So that's a huge issue, right? What are the data architectures? What are the privacy protocols? How are we going to learn about people's preferences without somehow invading them, right? Or even just making sure that we don't get hacked and, I don't know, I mean the royal we, how people don't get hacked and lose their data, right? So those are challenges. The other thing is, my next slide. Let's skip to my next slide. So this is not my beautiful slide. This is literally from Wikipedia, and I apologize. And I have to put that here because it always gets a laugh that I would take an image for Wikipedia. But this is a really nice, simple sort of diagram of what the grid looks like, right? Not what it looks like, but sort of what the layers are. So everything I've talked about in terms of large-scale wind, utility storage, utility-level solar, it's all happening up here at this high-voltage transmission system. Right? So that's where all this uncertainty is coming in. And then I turned around and I tried to convince you that we're going to manage this variability with residential and low-level commercial demand response, which is over here. Okay? The problem is these two systems don't really talk. Right? So the existing paradigm and operating for the independent system operator, so for example, the ISO New England, is they predict with amazing accuracy how much power they need to deliver at each of the substations that go down to the distribution systems. That's all they care about, right? So they don't talk to the distribution system. They don't know what's going on in the distribution system. And in fact, somebody from an ISO very recently told me they don't care. They don't want to know. Right? They've got enough problems that they don't want to deal with that. But if we are really going to leverage all those loads to help solve this problem, we have to figure out how to put those things together. So the physical structures are the same, really, right, between what we have now and what we will have, what we may have in the future, with the exception of the fact that we'll have more distributed resources and hopefully more coordination. But how we make those decisions really change, okay? All right, so what I have spent a lot of my time doing was thinking about how do we operate this piece of the grid under uncertainty, right? I'm kind of a mathematician. I do grid optimization under uncertainty. What do these new models look like? How do we operate that grid, and how do we make these algorithms are really, really hard to solve on large scale, right? So to solve it on a mini 9-bus thing is doable. To solve it on the New England power system is less doable. So when I started thinking about this lower level system, I said, how are we going to do it? So this is one of the things that we're working on, and I promise I'm not going to go into deep detail on this, but I wanted to make that point. So what we're doing is looking at bilevel stochastic optimization, and this is the idea. The idea is, so we have optimization models that solve the transmission system, and then the distribution system, they're all sort of radial, so they just do their own thing. but what if we could roll the distribution systems into this model, right? So that we're not like stylizing the distribution system and making it super simple and ignoring the detail, nor are we doing that to the transmission system, but can we put them together so they can coordinate their decisions and hopefully nobody loses, right? So what we want to do is sort of shoot for the same goal and allow the upper level, so allow the transmission level to make decisions that are informed about what's available at the distribution system, have the distribution system or the microgrid know what they could get for providing the kind of flexibility up into transmission, right? So that's the idea. What kind of information do we need to exchange? So we're thinking about sort of what is the demand response? So what are we paying the loads to adjust their behavior, and the energy price that goes from transmission to distribution? And what is the amount of demand response flexibility we could provide? And maybe under new FERC rules, we could actually provide some energy as well if we had some generation in the distribution system. So how does that work? Essentially, what we do is this is sort of a general formulation of a bi-level optimization problem, where you have your upper level problem and you reformulate your lower level problem. Right? This is a lower level problem in the blue, and then you can reformulate it into one problem. And I don't want you to know the details, but essentially this is the upper level problem that says, oh, this is our power flow, this is our cost minimization objective function subject to our limits of power flow on the lines, as well as what we can generate. We have to meet balance at all the nodes, right? Anything that goes in has to be consumed. And we also meet reserves, right? So we have some excess generation on there that we could use if we need it. And then this is the very similar problem for the lower level distribution system, where we'd have multiple distribution systems on this system. And they make decisions about providing either demand response up, right? So we increase our consumption, because that also might be necessary, right? If we're overproducing, for example, in our wind farm and we're expecting it, we might want some loads to increase a little bit, right, to balance that out. Or downward demand response, and sort of what those cost functions might look like and what would provide the incentive, right? So we can reformulate that into a single level problem subject to some conditions and convexity constraints. So if you want to talk about the actual nitty-gritty details of that optimization problem, we have a couple papers that describes how we incorporate the uncertainty into it as well. But I wanted to just give you this idea of, yeah, we'd have to completely change how we operate the system, but there are ways to do that, right? So we're testing it on some case studies, and I want to sort of tell you what this looks like, right? So advanced notice, we get sort of some reduction and reallocation of costs for the distribution system and the transmission system, but we are able to actually integrate more wind resources without causing reliability problems in the grid. And certainly there's impacts of subsystem size and location, right, in terms of costs and the wind capability. What kind of thing? I'm going to just go through very quickly. So interesting points. This is the cost for serving. So you have over a long time span. This is the cost to provide that electricity. This is the total system cost. The blue is sort of the traditional formulation where the system operator at transmission makes all the decisions, and they just provide the power to the distribution system, and they deal with it. And so you can see that it actually is a little bit less costly, okay, overall. And then the traditional formulation with the network. So in the traditional formulation that we use now, they don't include the network of the distribution system in that decision making, right? So if you include all the details, you add more constraints, it gets more expensive, and then the bi-level is in the green. So what are we taking away? Well, you can see here what's happened. If we use bi-level optimization, the transmission system actually ends up paying more, right? But the distribution system actually ends up paying less for multiple distribution systems. We can argue whether that's right or wrong. I think it depends who you talk to. Mathematically, it's correct. The transmission system operator may not necessarily agree that they should pay more, but on the other hand, in this case, now we're leveraging flexibility and demand response at the distribution level, so they're getting paid for that. So that's why their costs are going down. right? Because they're getting paid for the service they're providing. This is just normalized to the amount. It doesn't show anything new. It's just normalized to the amount of energy that's actually provided. The other point that I wanted to make is that you can actually incorporate more wind, right? So you can incorporate more wind without seeing the same level of cost increase across the system. So we can get higher levels of wind penetration, and we don't see the reliability problems that we had before. And is it scalable? So what do we get as we add more? So this is one transmission system and one microgrid, one transmission system, 3 microgrids, one transmission system, 5 microgrids, right? And so we see that the more subsystems that we have, the more flexibility we get. And that means that we see more benefits, right? So we see more benefits from doing this bi-level decision-making, cooperative decision-making, let's call it. You get more benefits from this cooperative decision-making as you add more subsystems in, right? So everybody wins because the transmission system gets more flexibility, and then the more systems we add, we get more flexibility, and then they earn more money, okay? So that just provides additional benefits. So the benefit of this approach is that all the systems decisions are directly kind of co-optimized between the systems. They can better leverage the load flexibility that they have. I would argue that the costs are allocated a little bit more equitably. We would have to talk about that in a little bit more detail, but sort of rough back of the envelope instinct, right? You provide a little more flexibility, you should pay a little less money, right? So I'll ask you to believe me on that. And then we have better ability to integrate wind, and the subsystem sizes are important. One other thing that I quickly wanted to talk about was the idea of microgrids that are now in the mix. One of these things that, I thought I hid that, but one of the things that we've also been thinking about my group is why, in every stochastic optimization model of any power grid ever, we always just minimize cost, right? What about maximizing environmental benefit or minimizing emissions or maximizing reliability, right? Those are all really valid points. So one thing that we're working on is looking for a method that allows us to sort of illustrate the trade-offs between revenue, emissions, demand response, or you could sort of use the inverse of that for reliability and see sort of what our trade-offs are, right? So I'm just going to tell you quickly what this is. So call this a metric for reliability. This is emissions, right? Lower is better. Lower demand response is better. More revenue is better. So you could see here that this is sort of your optimal point, right? Where you could do the best for all your objectives. But it's actually not possible, right? This is if you had all the perfect information so you had no forecast error, right? What would you do? Well, you'd make a lot of money, right? But you're actually polluting quite a lot, right? So there's this risk that if we think of everything in terms of cost, unless we had a really nice carbon tax, right? This would solve a lot of problems. Speaking for me personally, not for any institution. So if we had a carbon tax, that wouldn't be a problem. But you can see here, if we think about only one objective, we actually lose out on other objectives, right? And then these are all different, a whole host of other policies that we could choose that are sort of between these sort of single objective function kind of things, right? So you could choose any one of these policies in here for operating your microgrid, and it allows you to make trade-offs. And you can actually classify them. So this is a small number of policies that come out of this model, but it leaves the choice to specific stakeholders. So typically in multi-objective optimization, we say, I have 3 objectives and they're all equally important, right? And then we sort of reformulate it that way. But we don't know a priori, really, how to balance those objectives, right? So in this case, we actually don't do that. What comes out is, okay, these are different policy types. So this, I forget what they are. So policy type 1 is a high revenue policy. So you do this light blue policy if you really focus on earning money, right? And policy type 2 are low emission policies, right? So this blue one, right? You got your minimum emissions here, and this is sort of a balanced policy. So you, as a microgrid operator or a distribution system operator, could say, okay, I've talked to my stakeholders, all the stakeholders are in the room, and we've decided that this is the relative priority of the different policies, or the different objectives. So let's choose one of these and use that to operate, Okay, so the thing I like about this is that it doesn't make decisions for stakeholders up front, right? It says, let's look at all the possibilities, and then we'll let the stakeholders decide how we're actually going to operate. Again, I didn't want to go too much into depth, but I wanted to make the point that we talk about cost all the time, and we should think about other things. So happy to talk about that in more depth later, or share a paper or whatever. But since I asked the question, how are we going to get there from here, I feel like I should wrap up by answering that question, because I've brought up a lot of questions. But basically, it's parallel efforts, right? Obviously, we have to still continue to invest in all the renewable energy technologies to make them as good as we can, right? And not just do we make better blades, but can we make better power electronics to make them, better contributors to the grid? There's been a lot of growth in that area, actually, over the last several years. Developing smart home technologies and data management architecture, right? This is not just an engineering problem, obviously. Increasing system coordination to leverage those capabilities. We can't forget that we're still going to have to figure out how we're going to get some of that carbon out of the atmosphere, right? That's totally not my area of expertise, but we're going to have to do that as well, right? Because we've already got so much in there, it's going to be a problem. Big thing, and I know people have asked me at least once or twice today, what do I think the big barriers are to this transition? And I think the big barriers are not in the science. They're not in the engineering. They're in the social behavioral issues, right? And that's where we need to start leveraging everybody else who knows the answers to those questions, right? How do we change policy? How do we change behavior? How do we get people to engage and participate? And the thing that I think is overwhelming for engineers and mathematicians and scientists is these solutions are so context specific, right? So what's going to work in Hanover probably won't work 25 miles north of here, right? Like in terms of what the community wants to do, what the community accepts, what the community will participate in. And that goes for the whole continent, the whole world, right? So there's going to be very specific solutions that are going to have to be customized for a lot of places. And that tends to get really, really overwhelming, but probably there's, a subset of treatments, right? A subset of different types of communities that we could say, okay, you're probably one of these 10, right? And so we can sort of reduce the problem size that way, the way we engineers like to do. But, those are, I think behavior and policy are going to be the hugest pieces of these problems. So I haven't answered your question, really, but I think those are some of the important parts. And I'm going to stop there now and take any questions that you'd like to share.